Welcome to our second and final video on the Lognormal distribution. So in the previous video, we kind of introduced what a lognormal is, and we talked about some of the cool we solved for the expectation of it. So we actually did the integral out, did the Lotus calculation to solve for the expectation of the lognormal. So I'm just going to bring it a little closer. Okay. We're using the lognormal because it has some really nice properties when we're thinking about stocks, which obviously the Black Scholes, the point of the series, the Black Scholes formula is involved with stocks, and we'll talk about this video, why the lognormal is very useful for modeling stocks. So let's just kind of recap, and then we're going to dive into the topic of this video. So if you recall, if we start with a normal random variable x as mu, as mean mu and variance sigma squared, and we say y is a separate random variable, and we say y is equal to e to the x, so this is capital X, so e to the power of the random variable x, then y is log normal with then y is log normal with parameters mu and sigma squared. I'll write it like that, because these parameters are the parameters of kind of the underlying normal. And again, log normal means the log is normal. So if you took the log of this, log meaning natural log base e, if you took the log of this, you get log y equals x, and x is normal. So the log of y is normal, ergo y is normal. Okay, and we showed in the last video how the expectation of y, the mean of y, is e to the power of mu plus sigma squared over 2. We did out the whole calculation, and in this video, we're going to solve for the variance of y. Okay, so we did the mean, now we're going to do the variance. Both are going to be useful, and both will kind of give us more familiarity with what the lognormal is. So let's, in the previous video, we did a bunch of integrals and stuff. Let's see if we can go about it a different way. And let's start by writing out our expansion for variance. So we know that the variance of y, and I'm actually just going to plug in the variance of e to the x, because y is e to the x. The variance of e to the x is e to the x squared And this is, our classic formula for variance. The variance of x is expected value of the x squared, the expected value of that, and then the expected value of x squared. So the random variable squared, expected value of that, and then the expected value of the random variable squared. We can immediately make some simplifications. This just becomes e to 2x, right? And we actually have this term, right? We literally wrote it up here, expected value of y. Remember, y equals e to the x. So when we already have this term, we can just square it. Remember, by squaring it, we're just multiplying the exponent by 2. So this term is e to the 2 mu plus sigma squared. Okay, so this term is just this squared, right? So we just have e to the 2 mu plus sigma squared. So we just have to figure out this term. Okay, and you're seeing the expectation of a function of a random variable. We could do Lotus, we could do the big expansion and try to figure it out that way. Or we could realize that 2x has what distribution? Remember, x is normal with mu sigma squared. 2x is also normal, right? If you multiply normal by a constant, it's still normal. It has mean 2 mu and variance 4 sigma squared. And, you can think about calculating, expectation 2x, the 2 is going to come out, so it's 2 times the expectation of x, it's 2 mu. Variance of 2x, the 2 comes out and gets squared because it's a variance, so it's 4 times the variance of x, so it's 4 sigma squared. So if 2x is, normal 2 mu, 4 sigma squared, then we just have a log normal here. We have a log normal with the parameters 2 mu, 4 sigma squared. We want the expectation of that log normal. We could say now z, if z equals e to the 2x, we could say z is log normal. I'm just going to use shorthand. Looks like I'm running out of space. I'm going to use shorthand. Z is log normal. The parameter is 2 mu. 4 sigma squared. Did I run out of space? No. So if z is equal to this, z is log normal, 2 mu, 4 sigma squared. And we already know what the expectation of any log normal is. We just have to plug into that formula. So the expectation of e to the 2x just becomes e to the power of mu. In this case, mu is 2 mu, so 2 mu, plus sigma squared over 2. In this case, the variance is variance of the underlying normal is 4 sigma squared, so we get 2 sigma squared. Because we get 4 sigma squared divided by 2, you get 2 sigma squared. Awesome. So we have this term equals this guy, and this term equals this guy. We just have to do some subtraction. 2 mu plus 2 sigma squared. Because in the original, we're subtracting this expected value minus this expected value minus 2 mu plus sigma squared. These terms look very similar. We can factor out. This e to the 2 mu plus sigma squared. E to the 2 mu plus sigma squared. The second term becomes 1, right? Because that is the second term. And the first term, we basically have everything in the numerator except for this extra sigma squared. So it's just e to the sigma squared. Make sure you get that right. Yeah. So if you multiply these two together, you get an exponent of 2 mu plus sigma squared, which is 2 mu plus 2 sigma squared. Then the second term obviously is just e to the 2 mu plus sigma squared. These are equal. So awesome. That is our variance of a log normal. So we now have the mean and we have the variance. So for any log normal, if we have the mean mu, or if we have the mean mu or the variance sigma squared of the underlying normal, we can then find the mean and variance of the log normal. This is a little bit complicated, unfortunately. I don't think there's a way to reduce it more, but it's relatively simplified. It's nothing crazy. So this is a log normal. We kind of worked with it, got a sense of it. Remember that the log is normal. That's what log normal means. And what's really nice about the log normal for the purposes of modeling stocks is that it has a positive support. So this might, like the log normal might look something like, this is an infinity, but let's just say this is t or something. The log normal is only greater than 0, right? This is the log normal, whereas a normal distribution is going to go, the support of the normal distribution is negative infinity to infinity. So there will be values that are 0, which obviously when we're modeling a stock, stocks can't technically have negative value. So this doesn't make sense for modeling a stock. So that's why the log normal is very useful. Its support is entirely positive. Makes more sense for modeling stock. And you can think about why this support is positive. This will help you kind of wrap your head more around the log normal. Remember that the log of a log normal is normal. So the log of a log normal is normal. That means a normal to the power of e is log normal, right? If you raise normal to the power of e is log normal. If you raise all the values and on the support of a normal distribution to the power of e, e to the power of those values, you're only going to get positive values. Even e to the negative, 1,000 is greater than 0, right? So that's why you're going to get kind of all positive support from the log normal. So hopefully this made sense. The variance makes sense, and now you understand a little bit more about the properties of a log normal. So we'll see you next time.